We are live.
Okay, we are live.
Hello everyone. Ciao Fabio, ciao Marco.
Ciao.
Ciao.
Thanks for joining us. So today we have Fabio that will speak about the JVM Ergonomics. We are looking forward to hear more. You know us already, I guess. So we are the Ticino Software Craft Meetup. You can follow us on the usual channel. Meetup is the main one, and then we are on LinkedIn, of course, YouTube, where you can find the recordings, and then also on X. For the question, feel free to ask question in the chat on YouTube. We will see the presentation first, and then we are gonna stop and go through all the questions that you have asked so far. And I will say that's it. I leave the word to you, Fabio.
All right. Cool. So first of all, thanks for inviting me. Let's see if it's gonna be interesting as promised, or if it's gonna be me bullshitting about stuff I'm always interested in. But let's see. So we're gonna talk about JVM Ergonomics, and there is a subtitle here in the slide I want you to keep in mind throughout the presentation, because I want to connect to it at the end. But before JVM Ergonomics, maybe who am I? I'm Fabio, software engineer at Mollie. I'm Italian, living in the Netherlands. I always say that I moved here because of the sun and the food. Of course, nothing is real. So this is the lie I tell myself just to be able to stay here and do not complain too much. I'm not super social, as you might have seen from the slide. There is only LinkedIn, so that's the way you reach out to me. And before we start, I was asked to do some marketing of the company I work for. I work for Mollie. It's a Dutch. It's a fintech. It's born in the Netherlands. We are a PSP. It's a payment service provider. We also offer a bunch of financial services, and we have offices throughout Europe. But the most important ones for the audience today is the Netherlands, Lisbon, and Milan, which are our engineering hub. And of course, like, our engineering hub in Milan is the newest, the closest one to Ticino. And so you can see the vacancies. We are hiring. That's the team. And yeah, like, go ahead and knock yourself out with the vacancies. But let's dive into the real stuff. So this talk is going to be around a war story, basically. So I'm going to tell you how it started, what is the system, and then we're going to go through a bunch of optimization and discoveries we went through along the way. So let's start with the system. I work in merchant monitoring. It's a domain in Mollie in which we basically try to evaluate if anything weird is happening on transaction side, from merchants, from consumer, which are our merchants' customers. And for specifically monitoring transactions, we are sending transaction to a third-party supplier. And the system you see here is basically responsible to do just that. So there is something out of the picture here, which is a Spark job, which writes to the database, which is BigQuery, is in the bottom right corner. And then we have the system that kicks in after all the transaction has been written to BigQuery. Spark sends a notification into the pub subtopic you see on the top, the job notification topic, and the system starts doing its job, which is basically from the transaction repository reading the transaction that needs to be sent to the supplier from BigQuery, and basically enqueue them in another pub subtopic. There is a consumer attached to this pub subtopic that is basically getting the transaction, doing the adapting, and sending it to the third party. It's a REST API. It's quite straightforward, and we decided to do this way to have like a one-to-one mapping between transactions and events, so that if an event basically fails to go through, we can just retry because PubSub will redeliver, it will go to the dead letter queue, and so on and so forth. The problem with the system is that it's non-retriable. So as you can imagine, when we read the string from BigQuery, either we read them all or we don't read anything. So if the system fails midway through the process, let's say we read, I don't know, 25%, 50% of the transaction, and then the system breaks for whatever reason, the only option we have is to restart it fully. So we want to take like a quick fix to the problem. And the solution we came up with is to add yet another consumer. So the reasoning is that if we're gonna consume the transaction we are enqueuing from the transaction expository twice, we're gonna save them back to the database so that if during the next run, what we can do, we can be a bit more clever while reading from BigQuery. Instead of just reading them all, we can join with the new table we created and pull up only the transactions that indeed were not enqueued before. So that if the system goes through, let's say, 50% of its workload, then we can recover later on the rest of the 50% without the need of reprocessing half of it. The idea looks fine. The system was running fine. Spoiler alert, we are here. So after this thing, it didn't run as fine as before. And a few things to notice before we go to the next slide is that the system was doing its job in more or less 1 hour and was sending, on average, daily 1.5 million transactions to the supplier. So we created a new consumer. What can go wrong, right? Out of memory. And after we saw this, we said, okay, that's easy. That's something we actually overlooked a bit because we are adding a new consumer, right? We have a lot of parallelism in the process. Every consumer, every PubSub subscriber is actually configured to go with a parallelism of 100, which means that for every subscription, we have 100 threads. So by adding a single consumer, we added another 100 threads. And so we said, okay, more threads, no virtual threads. So every thread is actually a physical thread, which means that it's going to occupy more memory and stuff like that. We're getting out of memory. First thing you do, you go to Kubernetes and ask for more memory. This is not a great idea overall. It might be a great idea if you're panicking. And at this point, we were panicking because the system was not behaving that well, right? It was getting basically killed, so not performing the job at all. But notice that you can just go with whatever memory you want to put there because you're still limited by the node your pod is going to be scheduled upon. But we were lucky. We just increased the memory from 2 gigabytes to 4 gigabytes, and the system went through. All solved. End of the talk. Problem is, we started to look at the dashboard in Datadog, and we start seeing a bunch of weird stuff. This is the memory allocation of the system. The yellow line on the top is on the 4 gigabytes is the memory we put on the Kubernetes limits. But as you can see, the system is only occupying roughly 1 gigabyte. So already on memory allocation, that is something weird. Most importantly, the system is now taking 4 hours to terminate. And these are the metrics from PubSub. And there are 2 things to notice. One is, of course, that we are taking 4 hours. And I told you at the beginning that before the new consumer was added, we were roughly taking around 1 hour. And plus, this is the number of redelivers to the application. In PubSub, when a message is delivered to a consumer, there is a grace period in which basically PubSub thinks that if I will not receive any acknowledgement for it, I will assume the consumer is dead and I will redeliver it. So to guarantee at least once delivery. We are the consumer, there is no other consumer. The application is a single pod, so it's gonna receive the the message again, and as you can see from the y-axis, there are hundreds of thousands of messages being redelivered. So there are two things that we start thinking about at this point. One, our idea of being memory killed because of too many threads is probably not real, because as you can see, we are just, quote unquote, occupying 1 gigabyte of memory. And second thing is that probably we are CPU bounded, because if we are not able to hack the messages within the limit, which is 10 seconds, it's a huge time window, but still we are not be able to do so, probably we are CPU bounded. So let's look at the CPU graph. And it doesn't look that bad. I mean, we have 2 cores configured, which is the yellow line at the top. But as you can see from the profile below, we are not even using it super evenly. And apart from a spike at the beginning, we are not even using that much the cores that we asked the application, Kubernetes, to provide to the application. So there is something that is going really, really wrong with the configuration of this pod. So we start to investigate. We had a few roads to follow. We thought the code change was definitely an option, but at some point we thought about that big screen that maybe you saw if you're old enough when installing Java on a Windows machine or stuff like that. That there was a claim saying Java is running on 10 billion machines around the globe, and I was like, how is possible that only my pod is the slowest one? So there should be something I don't understand about the JVM that it's blocking us, or maybe it's the code, maybe it's just bad code. So we started investigating a bit, and we stumbled upon JVM Ergonomics. But what are JVM Ergonomics? The LDR is that it's sensible defaults. This is a quote taken from Oracle documentation. It's just a convoluted way to say that the JVM, when starting up, will look at the environment it's running in, and it's defining a bunch of defaults for you, which are most of the time good ideas. Because again, like Java is running on too many machines to be counted. So, and it's running fine. So either we have good performance engineers, or the work that the JVM folks did was actually fairly good. Disclaimer, this is not a comprehensive guide on JVM ergonomics. You will find, the more you dig, the more you'll find new flags, new corner cases, new tricks. This is definitely just like the tip of the iceberg. And I wanted to go through 3 of the flags we changed, which I think if you see the results, I hope you're going to be impressed as we were. So let's start from memory allocation. This is again the same graph I've shown you before, with the 4 gigabytes allocated limit, but only 1 gigabyte actually consumed by the application. Well, it turns out that in the JVM, if you don't do nothing, only the 25% of the allocated memory is used for the heap size. The heap size is the part of the memory that basically your application will use to create new object and do all of its work, basically. And so guess what? 25% of 4 is 1, and here we are at 1 gigabytes, almost full of application objects. So why we were getting out of memory, why we were getting killed by Kubernetes? Because before we have 2 gigabytes of RAM, and 25% of that is 500 megabytes, which is a good amount of memory. But if you're running hundreds of thousands of, maybe not thousands, let's say hundreds of threads, you're going to reach the limit pretty quickly, because each physical thread occupies more or less 1 megabyte. And if you do the math, you're going to reach 500 megabytes quite quickly. So we were getting out of memory because of the 2 gigabytes plus the 25%, and increasing it to 4 gigabytes gave the system that small amount of memory it needed to actually be able to perform the job, but we are already at its limit. So we can't grow more than 1 gigabyte here because it's the 25%. Since I'm obsessed with details and code, I did something probably stupid. I went to the OpenJDK GitHub repo and I tried to have a look at the code of the OpenJDK. And this is a sneak peek of the method that actually set the heap size. It's more than 200 lines long, so it was not fitting on the slide. But I think this is the gist. Like if you see at line 1499, the heap size, the reasonable max, is set through a flag that is called max run percentage. Plus on the lines below, there is much more, but I think this is really the gist. We need to check and use this max run percentage. After some digging on how the memory allocation work, not in the code, was too complex. I got this by countless searches on Google. This is a TLDR of how it works. So if you have up to 256 megabytes, 50% of the memory will be allocated for the heap. Between 256 to 512, roughly 125 megabytes is a fixed number. And above that, it's going to be 25% of the memory. And this is where most of the people will land, because if you are running Java in a Kubernetes environment, I assume you have between 500 and something more. But we will come to the details here, maybe toward the end. So first lesson, you're running in Kubernetes. Your application is the only one occupying that pod. Use the memory. It's for your pod. It's for your application to be consumed. So go nuts with it. Start with 75% is a good start, because again, like you're not, there is nothing else in the pod that is running apart from your application. This is not a very good idea if your application is not running on Kubernetes, or it's running alongside other things, because it means you're occupying a lot of memory that other application might need to consume, and you're allocating it for the heap size of the Java application. But for Kubernetes, since you're running alone, go nuts. 75 is a good start. You can go higher. Don't go too much higher, though. Did it work? I will say it did. Again, above you have the same memory usage I've shown you before, and below you see a new run of the system with the new default. We went down from 4 gigabytes to the original 2 gigabytes, changing the memory allocation to 75%, which now is around 1.5 gigabytes. But as you can see, we are not close to the limit as we were before. So we have still a bit of room for improving, let's say. So if we receive, let's say, a spike in number of transactions or whatever, the application can still cope with it, because it can allocate a little bit more memory. So that was it for the memory. Let's move on. Garbage collector. This is the second thing we start looking at. If you work with Java, you know what it is all about. If you don't, the TLDR is that you will never manage memory. You will never need to unallocate the memory you allocate, because the garbage collector will do that for you. And the caveat here is that most of the garbage collectors in Java do what is called stop of the world. So they will stop your application from running completely, and they will start basically creating a graph of your memory object, seeing if they are connected or not connected, and those unconnected ones will be removed. This is much harder than what I explained, much more complex, but this is really the gist. So what is the default? What does the JVM look for when setting up the garbage collector at startup? It looks at two things: the number of processors, keep that in mind, and the allocated memory.
up to 1791 megabyte, it will use serial GC. Above that, G1GC. G1GC is a very good default choice because it will work on a very good amount of cases, let's say. But serial GC might not be the best option because serial GC, as the name implies, is not parallel. It means that while building the graph, while cleaning up the memory, is doing it one node at a time, while G1GC, with the cost of a little bit of overhead, will clean the memory much faster because it's multi-threaded. Problem is, in Java, there are so many garbage collector implementation that it's stupid to limit ourselves to only these two. So these are, I've tried to summarize it a bit, but as you can see, the landscape is much more complex than just two garbage collectors. So while looking at the garbage collector, we saw that for parallel GC, there was the word batch workloads, which is exactly what our application is doing. So it's a batch. It's starting in the morning, doing some stuff, stopping, literally the definition of a batch job. And then we said, okay, let's try, like blindly. Let's see if it improves in any way the performance. So another lesson learned, be explicit with your garbage collector. The reason is, most of the time, maybe the one that Java gives you, it's fine, but you are aware of how your application is running. You know if it's a batch, you know if it's CPU bounded, you know if you can afford a stop of the word, you know if the overhead of the garbage collector might impact your throughput. So be explicit on the selection of the garbage collector. Problem is that at this point, I want to switch to the next slide and show you, like, did it work, as I did for the memory allocation. Unfortunately, we will not be able to pinpoint performance improvement only to the garbage collector because of many reasons. And the main reason is that we did too many experiments all at once. So don't do that if you want to experiment for real. But what I can show you is how the active processor count plus the garbage collector actually affected in junction the whole execution of the application. And also, active processor is something that strictly connects to the garbage collector, because if, as I showed you before, the default garbage collector is chosen upon two things: the number of processor and the memory allocation. But what are the number of what is number of processor? Theoretically, it's just a number. So if you call this get runtime available processor, you will get a straight number out of it. It can be 1, 2, 20, whatever. And it's going to be defined in many different ways in the JVM code. And I'm going to go through the details of it, but the very important thing to understand here is how it's used internally by the JVM and by frameworks. This number is basically used to size thread pools, which sounds like a very corner thing, but it's one of the most important things about this active processor thingy, because the number of threads in the thread pools is going to drastically impact your ability to increase the throughput. Because if you have more threads available, it will go faster. There are caveats, of course, but you will increase a lot the potential for your application to go nuts with the number of threads in the thread pools. But how is calculated? Well, in Kubernetes, it's quite simple. It's derived by the number of, basically by the CPU limit you define. And in Kubernetes, you define the CPU limits in millicores. So for instance, you say 100 millicores, and that's it. So before I go into how it's actually calculated, given the number of millicores, I think we need to go into what a millicore really is. Because before going into this rabbit hole, I had a completely wrong opinion about what millicore is all about. So let's take an example to make it super clear. We have two CPUs, a CPU limit of 600 millicore, and a period of a CPU period of 100 milliseconds. The CFS is the completely fair scheduler that Kubernetes uses to schedule activity on the CPUs, basically. So what it does is just divides the time in windows of 100 milliseconds, indeed, and within each window, it will allow you to consume your CPU limit. In this case, it means that within the 100 milliseconds, we are allowed, within each window of 100 milliseconds, we are allowed to consume 600 millicore. Also, this implies that millicores are not at all linked to the number of CPU our application is using. So let's make an example. Let's say that two HTTP requests comes to the application. Each HTTP request, let's say, takes 20 milliseconds and consumes 200 millicores each. So this means that at the end of the execution of those HTTP requests, we have consumed 40 milliseconds of the cycle. So we still have 60 milliseconds left. And we still have 200 millicore to consume as a budget within these 60 milliseconds that we have left. Then, of course, we are in a Java application, so guess what? The garbage collector kicks in. And again, it frees up your memory, super nice, but also consumes 200 millicore and 20 milliseconds. So at the end of the execution of the garbage collector, you don't have any CPU left to be used. You don't have any budget, but still 40 milliseconds in the period. So it means that you have to wait 40 milliseconds before you can yet again consume from the budget of 600 millicores. So this means that for the next 40 milliseconds, our application is being throttled by Kubernetes. And if a new request comes in, just needs to wait. It will wait for 40 milliseconds, and then it will be executed. Now, how it's calculated in the JVM? Well, it's basically a mapping 101 with the number of millicores. So from 0 up to 1,000, it's one CPU. From 1,001 to 2,000, it's two CPU, and so on and so forth. But I've just told you that basically this is not real, right? So 100 millicore doesn't mean one CPU. It just means your budget within a time window. So what do? You just lie. So I think this is one of the few options that you have in your life to tell a good lie, so nobody will complain about you lying. Just tell the application, tell the JVM that the number of active processor each is much more than it thinks. A good start might be to double the amount of CPU limit. For instance, we went to 2.5 millicore, 2,500 millicore, and so we set it to 5. So 5 active processor with a limit of 2,500 millicore. So how the garbage collection changes and the active processor changes affected the workload. So let's start from the CPU usage. Again, above I have the execution before the changes and below the execution after the changes. So as you can see below, the CPU is consumed much more nicely. Like before, we had a peak at the beginning, and then we were not going above one core basically. Now there is still the peak; it's still recognizable, but the CPU consumption is more even throughout the execution of the process. What about the number of unhacked messages, or better, the messages there are not hacked in time? Well, basically they went down to almost 0. There are still a few at the startup, but also, and this is the most important thing, notice the times on the x-axis, and you will figure out that basically we went back to 1 hour.
maybe this is also more visible from these graphs. These graphs are 2 graphs from the application running with the new setup, so with all the JVM optimization that we talked about. And as you can see, the line of the CPU consumption is quite nice throughout the process, as we discussed. But also, as I showed you before, there were still a bunch of messages that were reaching the act deadline in the beginning. And you can actually see this from the graph below. The graph below is representing the throttling. This is something we discovered along the way, that is actually a metric that Kubernetes exposes you that tells you for how many seconds the throttling take place. So don't get fooled, as we were in the beginning, from the fact that the application is hitting the CPU limit. This is not an indication of the application being throttled, but look at the actual metric of throttling. And as you can see, we are being throttled throughout the process, but there is a clear peak at the beginning. But I can't tell you why this is happening. Like, we reach good enough performance, we stop investigating. The return on investment was not that great at that point, but since we went back to 1 hour of execution time, we call it done. Of course, the more you dig, the more you figure out things that are not going well. But this is it. Like, we changed 3 things. We changed memory allocation, garbage collector, and active processor count. We didn't change any lines of code. You ask me, did it work? I will say this was a success. So what? Like, what do I take out of this? This is how we run application in Mollie at the moment. So we just do java -jar app.jar. We don't specify anything, which means we are relying completely on JVM Ergonomics. But if you didn't listen so far and you want to get something out of this today, please don't do this. Like, this is so wrong to many levels. And in fact, this is what we are working on right now. We are working on defining some custom defaults for our application because we know them better. And I was so obsessed with this topic that I went to see a YouTube video, which is linked in the slides that I'm going to share with you later. It's not a talk, it's like a workshop, because it's like 2.5 hours long from Microsoft, talking specifically about JVM performance tuning in Kubernetes environment. And at some point they show this kind of research from New Relic on about more than 10 million JVM running in production on Kubernetes. And as you can see from the numbers on the top, like 72% set the XMX flag, which is another way to set the heap size. Instead of setting it by percentage, we'll set it by actual number of bytes, so which is still is still good, much better than not setting anything, which is a good thing to do. But 72% is high, but not very high. If you see the number below, 27% not setting anything related to the heap size means they are defaulting to the 25%, most likely, depending on the memory allocated, on the 25% of the heap size being allocated on top of that memory. And also, it has implication on the type of garbage collector used, because if you see 41% as less than 1 gigabyte, which also means that since it's below 1.7 gigabytes, it will most likely be serial GC instead of G1 GC. Then this is another interesting one. The one on top is about the number of CPUs that are attached to containers. And as you can see, almost 60% of them has only one. And one CPU means one active processor, which means that your thread pools will likely have very few threads available in the thread pool itself, because they're going to use the number of active processors to set it up at the beginning, unless you have some customization on the thread pools.
And also below, you can see that 65% doesn't even set an explicit garbage collector algorithm, which again might mean that you're getting serial GC instead of G1 GC or whatever. So TLDR, do not run java-jar app.jar. Set your defaults, think about it. You are a software engineer, most likely. If not, it's fine. The fact is, we, as software engineer, we write the application. We know what the application is all about. We know if it's memory dependent, if it's more relying on CPU, if throttling is a problem, is throughput is what we have to improve. This is like our job, right? Like we write the application and we know how it should behave. And so this is the hint you need to take to define very simple tuning on the JVM. It's just a matter of changing 3 flags and the life of your application will change drastically. A good starting point, as we went through the talk, is definitely set 75% for the max run percentage. Definitely lie on the number of active processors, especially if you have less than 1000 millicore, because it means only one active processor. And also if you have less than 7091 megabyte, use something else, like be explicit on the garbage collector you want to use. And this is it.
Nice. Thank you, Fabio. This reminds me, there is like, I will not say a story, but usual post on LinkedIn where there is a person who is called for fixing something with a screwdriver. He does like half of the cycle and ask for a bill of 100 euro.
Yeah.
And the person complains, "Oh, you are asking 100 euro for half with the screwdriver?" And he answers saying, "I know, I studied, days to
I know which flags to set in
what
the
I had to
JVM
do." Very nice. So there was a couple of questions, but I believe you answered, because one question was from me asking which Java version you used, but then Paolo said the Java 21. So maybe you said and I missed.
No, I don't think I said it.
Okay.
But maybe I did. I'm not sure. But yeah, we are using Java 21. Okay. I think at the time we developed this, we were using 17 because we are of the LTS. We went to 21, and actually this is a good moment to probably mention the virtual threads, because with Java 21 you have also the possibility to go nuts with virtual threads. We didn't experiment, but maybe just by switching to virtual threads would have been maybe not enough, but much better, let's say, because the virtual thread is not consuming 1 megabyte per each thread you're going to create, right? Because it's not a physical thread. It's the JVM that maps multiple threads on the same physical thread. So in terms of memory allocation, this is going to probably definitely it's going to be better.
Especially when, we are speaking about IO bound problem. That's definitely helpful. Okay. No, indeed, I was curious because even the default or the GC are changing in every version. So also
these one are quite stable. I chose to tune stuff that is quite stable. Also, depending on the vendor of your JDK, those are going to be different. If you're using Azul versus OpenJDK versus Correcto, they have different defaults, because the JVM is thought to be used in a different environment, right? So Correcto probably it's more for, since it's from AWS, they want to run everything in Kubernetes, I'm assuming, just to give an example, and they will set different kind of defaults. But usually
Garbage collector, and memory allocation, those are quite stable across versions of JVM. One thing you can do if you have the possibility to change vendor, try with different vendors. We didn't, because we are, let's say, stuck. We made the decision of using Azul, and that's the only JVM we are allowed to use. But if you can experiment with more, you will definitely see changes in terms of performance.
I have a question related also to this. Do you have a tuning environment in which you can test this kind of configuration? Or it's just, okay, ship it in production and then let's see what happens?
Yeah, good question. Actually, we didn't want to ship it and pray, but sometimes we did, because it was very hard to reproduce exactly the same load profile in stage. We did it at some point in stage, but it took so much time that we just thought, okay, we are wasting much more time experimenting in stage rather than just ship it to prod and see how it goes. I mean, it's not the odd path. It can fail, so we can afford the application to fail, and we're going to recover it later. It really depends on the type of application you're handling.
Yeah.
For us, it was like a piece of cake. We can break it, we can recover it later. There is no customer waiting for this to finish, right? Otherwise, I think you need to invest much more time doing it in stage just to be sure.
Yeah, even the deployment model, if you are using a canary deployment, you can just try on several pods and then ship it.
For us, it was really easy, right? Because it's just one pod, so it was the perfect experiment playground. But if you're trying to experiment on a much bigger application with maybe 10 pods, dozens of pods, it's possible. You can roll it out with a canary, as you said, and just monitor the change on those pods. You just need to maybe prepare a bit more in terms of your observability.
Interesting.
Understood. There was another question which I believe you answered, because Paolo asked why you didn't use XMX, but you answered because it's a way, as you said, to set.
Yeah, it's just another way. I just saw online that like max run percentage is much more recent compared to XMX. XMX was there from basically probably day one, and so people are used to use that. Max run percentage, I think, was added more recently alongside with the use container something. There is another flag that actually tells the JVM you're running in a container, so behave differently. And I found by searching online, because again, this is not science. This is like an art. Performance tuning, the more you do it, the better you get. And it's very hard to just say, this is the thing that works, because it works for you in your environment, doesn't work generally. And I just saw people recommending to go with the max run percentage. But then if you have a specific workload and you want to have real control over the size of the heap size, the only way is to use the XMX flag, which is still better than nothing. The important thing is set it, be explicit, be aware.
Okay, I was looking if there are other questions. So okay, Paolo was just a note when we were speaking about the virtual threads. He said that, of course, the side effect, we can have side effects, so all should be tested.
We actually tried a few things on Java 21, because at some point Spring enabled the usage of virtual threads, and I think we stumbled upon this specific problem of thread locals behaving weirdly, and so we just said, okay, this is too much. Let's go back to the classic
physical threads for now. Probably we are not ready for this. But yeah, like it's still it's there. It's 1.0. It's generally available, but it's I think we need to wait a bit for the frameworks to get used to those virtual threads.
Makes sense. Then we have Tiziano saying that, yeah, Datadog is a fully complete solution for metrics and benchmarking like that. If you can suggest some open source tools for this purpose.
Well, for the usage we did of Datadog, I think even if you have something like Grafana, is more than enough, because we didn't actually use a lot of Datadog resources. Like we didn't check spans traces. We didn't create fancy graphs that you can only create in Datadog. It's just having a place to look at the Kubernetes metrics mostly. We were relying a lot on that. We were relying on maybe the only real thing we used in Datadog is that it comes with a nice JVM dashboard, which is tailored on understanding like garbage collector cycles, threads count, and stuff like that. But I'm pretty sure there is something out there, even open source, I don't know, for Grafana, so you can set up a good JVM metrics dashboard.
Okay. I don't see any more question. So yeah, I think we are good.
Nice.
Then we can close up, I guess. Yeah, I was waiting a few more seconds, but I think we are good. Thanks a lot, Fabio. It was super interesting. It was a pleasure to have you in our meetup. And for all the others, I think we are gonna do something in September. See you. Bye-bye.
Bye-bye.
Bye-bye.